Section 5.1 starts with a review of the natural log function. So when we talk about the natural log, we're talking about the function y equals the ln of x. Remember that the understood base is base e, and e is one of those irrational numbers, never stops, never repeats. It's approximately 2.71-ish, similar to pi in that respect, that it never stops and never repeats. So we're going to do a brief review of that. I've got a more extensive review in other videos where you could go in and review all of your log properties and exponent properties. So just to do a really quick review, natural logarithmic function, the domain is from 0 to infinity. Notice it's not including 0. The range is going to be all real numbers. If we were to graph this function, it would look like this. It has a vertical asymptote at x equals 0. The function is continuous. It's increasing and it's 1 to 1. And the graph is going to be concave down. When we talk about log properties, if we take the ln of 1, then we're going to get 0. That's true for any base. We have a property that says if we take the ln of AB, that's the same thing as splitting that up into the sum of two logs, ln of A plus ln of B. Once again, we could do this with other bases. This property holds. And I'm just going to call this B1 just to let us know that it's not the same as whatever that base is. We have a quotient property. I'm going to talk about property 4 next, where if we're taking the ln of a quotient, we can split that in between, split that into two logs and subtract the two. That also works with any base. Instead of using AB, I'm going to use mn here. So that would be the log base b of m minus the log base b of n. And then we have that power property in 3, where we can bring that power to the front. That works for any base also. So I just want to play with those properties a little bit. I'm going to go to the next page and we're going to talk about expanding and condensing. So in 23, they're asking us to expand this out. The first thing we see is that division bar. So we could rewrite this as the ln of xy minus the ln of z. And then we can split that product up and write that as the sum of two logs. So that's fully expanded. 25. We have x times the square root of x squared plus 5. So we could rewrite that as ln of x plus the ln of the square root of x squared plus 5. Square root's the same thing as a 1/2 power. So we can pull that 1/2 power to the front. So that's fully expanded. And then 27, we have the ln of the square root of x minus 1 over x. So the big thing we see here is that square root. That square root is a 1/2 power. So we can pull that 1/2 to the front. And then we could rewrite this, since this is a quotient, as the difference of two logs. Okay, but all that's going to be multiplied by 1/2. We can also talk about condensing, combining things into one log. So this guy is a power, this 2 is a power, and this 4 is a power. So if we were to rewrite this, we have the ln of x cubed plus the ln of y squared minus the ln of z to the 4th. So now we have a product. So we could rewrite that as the ln of x cubed y squared minus the ln of z to the 4th. And then we could write that as the ln of x cubed y squared over z to the 4th, combining all of those pieces into one logarithm. When they say condense, we want to write it as a single logarithm. So if we look at this one, here's what I see. I see that I can rewrite these two, and I can factor a negative out of both of those. There's a lot of different ways to think about these. This is what I see when I look at it. Now I see I can put these two together, and that's going to use that property that takes the sum of two logs and combines it into a product. So it's going to be the ln of x plus 1 times x minus 1. And then we can rewrite that as the ln of x squared plus 1 minus the ln of x squared minus 1. And then we can put these together using that quotient property. And then finally, we can move that exponent back where it belongs. So that's a really, really quick review of just condensing and expanding logarithms and logarithmic properties. I've got a more extensive review in Blackboard if you want to take some time to look at those videos. That really slows down that entire process. So if you feel like you need to review, you definitely have a place you can do that in Blackboard. So what I want to do now is start talking about the calculus behind all of this. Anything that we have done in the previous chapters, limits, derivatives, finding equations of tangent lines, integration, we can do that with all of these transcendental functions. And the first one we're actually talking about is your natural log function. So we're going to see all of that stuff come back. We're just now throwing in some new rules, really. So let's look at this one. We want to find the limit as x approaches 3 from the right. So this accidentally got cut off here. So find the limit as x approaches 3 from the right of the ln of x minus 3. We could graph this guy on the calculator, and what we're going to see is that this is a transformation of the ln of x. So ln of x looks like this. The transformation, that minus 3 is going to shift this graph to the right 3 units, which means that that vertical asymptote, which was at x equals 0, has now shifted to x equals 3. So then this graph's going to look like this. And we could also, like I said, graph this in the calculator. You're going to get the same kind of graph. Now they're asking us what happens as x approaches 3 from the right. Well, if we come in from the right-hand side, we're coming in from this way, and we follow that graph, we see that all those y values are getting closer to negative infinity. So we would say this has unbounded behavior, and it's heading to negative infinity, which makes sense because we would see that vertical asymptote at x equals 3. Anytime we have unbounded behavior, remember we always have a vertical asymptote there. 42 is asking you to take the limit as x approaches 5 from the right of the ln of x over square root of x minus 4. The first thing you always want to do is ask, can I plug that number in? So if we were to plug that number in here, we're going to have the ln of 5 over square root of 1, which is going to be 5 over 1, which is going to be 5. So we're taking the ln of 5. So this is not a very nice number. We could type it in the calculator and get some kind of idea of what that would look like in terms of an approximation. But we want exact values, so we're going to leave it as the exact ln of 5. If we wanted to, we could graph this guy on the calculator and look at what happens as we get close to 5 from the right. So we could plug in numbers like 5.1, 5.01, 5.001. And what we're going to see is that we're going to get really close to that ln of 5. But remember, your calculator is not designed to give you exact values, and we're going to almost always want that exact value. So now let's go back and talk about the derivatives. If we want to take the derivative of the natural log function, ln of x, it's going to be 1 over x. Now keep in mind, because the ln of x had a domain restriction, then this derivative has to have a domain restriction also. ln of x, remember if you think about that graph, has a domain of x is greater than 0. So then that domain restriction from that function has to follow us to the derivative. That's why x has to be greater than 0 for the derivative. This cannot have a different domain than what the original function had. So likewise, we can also use the chain rule. If we did a u substitution, then the derivative would be 1 over u times that derivative of u. And we're used to seeing that du over u. And they're using the prime notation here. So let's look at a few examples. Let's say we want to take the derivative of ln of 3x. We can use a u substitution here. So we're going to let u be 3x. So du would be 3. We would do our substitution. We're taking the derivative, I'm going to write it this way, y equals ln of u. So our derivative would be y prime equals du over u. And then if we sub back in, our du was 3 and our u was 3x. So our answer will be 1 over x. So there's our derivative. Let's look at 45. We can do the same kind of thing. Let's think about what u is. We can let u be x squared plus 3. So du would be 2x. We're going to do our rewrite. The rewrite would say f of x is equal to ln of u, or we could use y. The derivative of the ln is always du over u. And then if we sub back in, our du was 2x, and our u was x squared plus 3. So that's taking that derivative using the chain rule. Let's look at 47. We have y equals ln of x to the 4th. We want to take the derivative, so let's think about our u substitution. We're going to let u be that inside function. So in this case, the inside is ln of x. So let's do our rewrite. We have y equals u to the 4th. We also need du. I forgot to find that. So when we take the derivative of the ln of x, it's just 1 over x. So we've done our rewrite. Now let's take the derivative. The derivative is going to be 4 u to the third, that's the power rule, times du. And then if we sub back in, we're going to have 4 times ln of x to the third times du, which is 1 over x. So some of these are not going to be very pretty, but they're fun. Let's look at 49. 49 is y equals the ln of t plus 1 squared. Now we can use our logarithmic properties to help us simplify this just a little bit. Let's pull that 2 to the front since that's the power rule for logarithms. So we can rewrite that way, which is going to make life a little bit easier. So now let's talk about our u substitution. Let's let u be t plus 1. The derivative of that would just be 1. So if we do our rewrite, we're going to have y equals 2 ln of u, derivative. The derivative of y is y prime. Then we have 2 times the derivative of ln of u, which is du over u. And then if we sub back in, du is 1, u was t plus 1. So our derivative, I'm going to simplify this, is 2 over t plus 1. Final answer. So now let's start combining some of these rules. Let's look at 54. We have f of x is equal to the ln of 2x over x plus 3. So we're taking the ln of all of that. There's an understood parentheses there. U is always the inside function, so it's 2x over x plus 3. If that's u, then du would be the derivative of that. But that's going to involve the quotient rule. Quotient rule says it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. We can simplify this. This is 2x plus 6 minus 2x over x plus 3 quantity squared. And notice those two x's cancel, so we're left with 6 over x plus 3 quantity squared. So we have u, we have du. So now we're ready for our rewrite. So our rewrite would say y equals ln of u. We're just doing our substitution in for that piece. The derivative of y is y prime. The derivative of ln of u is du over u. And I'm going to write this just a little bit differently to make this a little bit easier. So this is du times 1 over u. Let's try to avoid complex fractions if we can. So if we look at this, du was 6 over x plus 3 squared. And we said u was 2x over x plus 3. So we still have a complex fraction, but I don't think it's as bad as it could have been. If we simplify this guy, we do keep, change, and then flip. That becomes x plus 3 over 2x. So we see some things are going to cancel. The x plus 3s are going to reduce. We have an x plus 3 in the bottom. That 6 and that 2 will reduce. We have a 3 in the top. And we still have an x in the bottom. So there's our derivative for that guy. And then let's look at 58. We have y equals the ln of the ln of x. So doing a u substitution, we're going to let u be the ln of x. So that's that inside piece here. du is 1 over x. We can do a rewrite. So this says y equals the ln of u. Then we're going to take the derivative. The derivative of y is y prime. The derivative of ln of u is du over u. And then we're going to do our substitution back in. du is 1 over x. U was ln of x. So this can be rewritten this way. And that's going to reduce. Remember, keep, change, flip. So our final answer is 1 over x ln of x. There's our derivative. So this is one where we could have benefited from what we did last time. Rewrite this as du times 1 over u. Okay, algebraically, that's the same thing. So then if we would have done our substitution, du was 1 over x. 1 over u would be 1 over ln of x. So you can see how we would get the same thing.